the question. A certain hydrocarbon on complete combustion at standard temperature and pressure STD produce 89.6 dm cube of CO2 and 54 grams of water. The hydrocarbon should be what? Because it's from understanding the question we will know the approach with which we will go about solving the question. From here, we understand that we are trying to get the amount of a hydrocarbon in terms of its formula. And with regard to that, we are talking about empirical formula. But empirical formula is not the only thing that will play a role here. We have to use what I prefer to call mass fraction to get the exact mass of the hydrocarbon, because the question says hydrocarbon. So there are things that I would want you to take note of: the hydrocarbon, complete combustion, and STP. These are the sensitive informations that was given to us that we will use to solve this problem. First of all, the question says a certain hydrocarbon, meaning that the molecular formula or the empirical formula would be a combination of carbon and hydrogen. A certain hydrocarbon, strictly carbon and hydrogen, and that's what uh, basically makes up the hydrocarbon. And we can see from the option that is carbon and hydrogen on complete combustion. And we know that on complete combustion of hydrocarbons will always end up with CO2 and water. So on complete combustion, we have CO2 and water, meaning that the product of the combustion is um, strictly CO2 and water. That is no other product. That's what this implies. Then the next point is at STP. This at STP is important for us to be able to get the amount in mass of carbon dioxide that was released. Alright, at STP, this is the volume of the gas that was released. First of all, let's go about it this way. Let's try to get the mass of carbon. The mass of carbon in the CO2 that was released. Let's try to get the amount of carbon in the CO2 that was released. And we will use what, like I said, I prefer to call mass fraction. But before we go over to mass fraction, we have to take note of this point here at STP. What does it mean at STP? This is what it means. We know in chemistry that at standard temperature and pressure, 1 mole of a gas occupies 22.4 dm cube by volume. From there, we can get how many moles of the gas that are present in 89.6 dm cube of CO2. This is the simplest way we can go about it. For the sake of time, let's just go straight to solving the question. We know that 22.4 dm cube of CO2 is equivalent to 1 mole. Let me put it this way. Let me just put it this way. And now the question is 89.6 dm cube of CO2 be equivalent to what? We know that 22.4 dm cube of CO2 occupy 1 mole, or 1 mole of a gas is in 22.4 dm cube of CO2. Then the question is how many mole of that gas is in 1 dm cube of CO2? How many moles of CO2 is in 1 dm cube of CO2? And for us to get that, we have to divide this mole by this volume. And to be able to do that, we have 1 over 22.4. And this represents the amount of CO2 in 1 dm cube for each dm cube of the gas. And here we have 89.6 dm cube. So if this is the amount of CO2 in 1 dm cube of the gas, so the amount that will be in 89 will be this times this. So that means we will have 1 over 22.4 times 89.6. And that's equivalent to, or we can just write it to be 89.6 over 22.4. Let's punch our calculator. 89.6 divided by 22.4, and that will give us 4 moles. So it means that we have 4 moles of gas. We have 4 moles in 89.6 dmq. This is just a step amongst many other steps we are going to um, go through in this calculation. Now let's go to the next step. We have gotten the number of moles of CO2 that is present in this 89.6. So the next thing is to convert these moles to mass for us to get the mass of CO2. And once we get the mass of CO2, we use what I consider the mass fraction to get the mass of carbon in the CO2. And from there, we also get the mass of hydrogen in water, and we now apply our empirical. So we know that we have 4 moles of CO2 here from the calculation, and we have to get the mass that these 4 moles represent using the formula number of moles is equals to mass over molar mass. All right, we have a number of moles to be 4, and we have the molar mass of CO2 to be um, 32 plus 12, and that should give us 44. So we have mass over 44, and therefore the mass of CO2 is equals to 4 times 44. And punching your calculator, 4 times 44, we have 176 grams. So we have 176 grams of CO2 that was released from the combustion. Okay, having got the mass of CO2 and we already have the mass of water, the next step is to use mass fraction to get the the mass fraction of carbon and the mass fraction of hydrogen. We know that H2O is 54 gram and CO2 is 176 gram. Now we have to get the mass of carbon here and the mass of hydrogen here. And first, let's start from hydrogen. To start from hydrogen, we know that this is the molecular representation of water. And what this means is that if we are considering this in terms of a mole of water, that means we have a 2 moles of hydrogen and 1 mole of oxygen that reacted to give us 1 mole of water. And we will use this fraction and their molar mass in order to get the mass fraction. Um, just follow me through, you will understand what I mean. First of all, we have to get what is the molar mass of water. We know the molar mass of water to be 18. We know the molar mass of water to be 18. And we have to represent this in terms of mass fraction. Now, we can represent this in terms of mass fraction of hydrogen in relation to water or oxygen in relation to water. Any of them, we can get it. And if we represent this, let's say we are representing it with hydrogen in relation to water, the mass of hydrogen here will be 2 grams. So that means we have 2 over the total mass, which is 18. This is mass fraction of hydrogen in relation to the water. And this mass fraction is constant for every given amount of water we have. If you know that, we now have to get the mass you need. This mass or this ratio is constant or approximately constant for every given mass of water we have. So what it means is that if we have 200 grams of water in a cup, the amount of hydrogen there, if we put it in this form and simplify it, we will arrive at this. And if we have to simplify this more, we still arrive at 1 over 9. So this is like the mass constant. And we will use this to get the mass of hydrogen in the gas. So we know that for every given mass of water, the mass fraction of hydrogen will be 2 over 18. So we have to compare this to the given mass of water that was given to us. And that would be, we don't know the mass of hydrogen in this, but from here we can be able to calculate the mass of hydrogen, which is x over 54. And the next thing to do is to cross multiply. So here we have 18x is equal to 2 times 54. Now punch your calculator to get the value of 2 times 54. And 2 times 54 is 108. So we have 18s is equal to 108. To get the amount of hydrogen we have will be equal to 108 over 18, which will give us 6. So this is the amount of hydrogen in the 54 gram. The same method we apply here is the same method we are going to apply to get the mass of carbon from the CO2. Now let's go over to getting the mass of carbon. All right, now to get the mass of carbon from here, we'll apply the same method we use. So we get the mass fraction of carbon in relation to this whole thing. And here, carbon is 12, this whole thing is 44. And we have x of carbon over 176 gram. Where we may know we don't really need this gram anyway. This will cancel this, we'll have this, and this will go what's the unit we need. Alright, the same thing we do, we cross multiply. We have 44x is equal to 12 times 176. And 12 times 176 will give us have 44x is equal to 2112, and x will be equal to 2112 over 44, and that will give us 48 grams of CO2. We have already gotten the mass of hydrogen to be 6 grams and the mass of carbon to be 48 grams. Now we conveniently apply our empirical formula, and that's actually what the question is asking us. Now, applying our empirical formula, we place hydrogen here and place oxygen, carbon at the other side, and hydrogen will have 6, carbon will have 6, carbon will have 48. So from here, the first step in empirical formula is converting these masses to their respective moles. And mind you, solving stoichiometric questions from the standpoint of moles are more convenient and more safe. Alright, so here to convert this to mole, we divide it by the molar mass, which is 1, and this we divide by the molar mass, which is 12. And dividing this, we have 6, and this will have 4. The next step is now to divide by the one that has the lowest value, and the one that has the lowest value is 4. So we divide through by 4. Here divide by 4, here divide by 4, and we have 1, and this will have 1.5. But it is convenient for us to run this thing up to the nearest whole number. So we have to find a way of multiplying this in order for us to get the nearest whole number. We have followed the step. We have 1.5 and we have 1. And returning this to the nearest whole number that we can get, you will observe that if we return this to the nearest whole number, we still get back 6 and 4, because the most convenient nearest whole number we can return this to is by multiplying both sides by 4. When we multiply here by 4, we have our 6, and when we multiply here by 4, we have our 4. Mind you, I just have to do this so that you will bear it in mind that sometimes the nearest whole number will not return you back to this. Alright, our empirical formula is now C4H6, and this is the simplest formula of the compounds. We now go to the option and find the option that corresponds with this answer. Here A66H6, which is not the answer. B is C4H10, not the answer. C is C5H10, not the answer. And D is C4H6. This is the answer. And we have come to the end of this. Thank you for demystifying the chemistry